Hello everyone, welcome to FutureSat. My name is Rev. I'm a physics master's student here at Brown. And today we'll be talking about a satellite that can take a picture of a black hole. So so gonna get started. So let's get into it. So this presentation is broken into 4 sections. First, I'm going to talk about what is a black hole, okay, for the unacquainted. And then I'm going to talk about how to take a picture of a black hole, which is easier than you might think. All you have to do is take your phone and snap a picture. And then I'll talk about how to image the photon ring of a black hole. And lastly, we'll talk about how Brown fits in here. So let's get into it. Okay, so what is a black hole? Okay, so a black hole is like a vacuum cleaner in space. So this is a black hole, and a black hole has 2 important points. It has the event horizon, that's this region, the circumference of the black hole, beyond which nothing can escape the black hole, and the black hole has a singularity at its center. Okay, so anything that trespasses this event horizon can never exit the black hole again, right? So even light itself, if it trespasses this event horizon, it's forced to hit the singularity like this. So that's what you see in this diagram right here. You have the black hole's radius, and you have its event horizon and singularity. The next important part of a black hole is called the photon sphere. This is the last place that light can circle a black hole. So this is actually outside of the event horizon. It's 3 times the short shell radius, and that's what you have here, the photon sphere. That's the last stable circular orbit for light to travel around a black hole. So this is the photon sphere. And so if we want to characterize a black hole, we need only 3 things. Now this is getting really boring, so let's spice it up. See, I'm a human, right? And I have different properties that you could describe me by. I wear glasses, right? I have a certain hairstyle, certain ethnicity, certain gene color, whatever, right? I have different parameters you could describe me by. But for a black hole, you need only 3 things to characterize the entire black hole. You only need to know how heavy it is, its mass, how much charge it has, Q, and how fast is it spinning. That's it. So even though black holes form from these insane astrophysical processes where you have a supernova of a heavy star, all of that information is lost. To characterize the black hole, you only need these 3 things. So let's get into it. First of all, how heavy is the black hole? That determines how big it is, its radius, by what we call the short shell radius, right? So the short shell radius of a black hole, this R sub s, is directly proportional to its mass. So the heavier your black hole, the more massive it is. That's mass. What about charge? How does the charge of a black hole come in? Well, let's say you have a positively charged black hole. Maybe somehow during the formation process of this black hole, it swallowed more protons than electrons. For those of us in the audience who are taking E&M, don't shoot me because I might make some mistakes. But let's say there's some negative charge near the black hole. This black hole will quickly neutralize on the order of 1 microsecond. So that means charged black holes don't last very long. Astrophysical black holes will almost always be neutrally charged. And the last parameter of a black hole is its spin. Now, if you've heard of quantum mechanics, you might be a little phased here, because is this the orbital angular momentum of a black hole or the spin angular momentum of a black hole? This spin is actually the physical rotation of the black hole itself. So it's not any kind of quantum angular momentum. And so how do we characterize the spin of a black hole? Well, if you've taken a bit of physics, you might know angular momentum is just mvr. It's a vector. There should be a cross product there. If I didn't make these slides at 11:59 last night. But to characterize a rotating black hole, we use something called the Kerr metric. Now this looks very nasty. Looks worse than my future, actually. But But the idea, what this equation is telling us, is simple. If you have a black hole that's rotating, the black hole's event horizon gets squished, almost like a pizza. If you've ever seen how a pizza is made at the pizza store, then you might see when the pizza maker spins the dough, the pizza stretches out, right, as it starts to rotate. That's what's happening here. As the black hole starts to rotate, it stretches out, and the event horizon is no longer a point, it's actually a ring here. Why is it a ring? Because a point can't spin. A point, if it had angular momentum, it would have to have infinite angular momentum because the radial extent of a point is 0. So that's why the singularity now goes from a point to a ring. Okay. So in real life, most black holes are spinning, and not only are the black holes spinning, but the stuff around the black holes is also spinning. So that's what you see here. This is the accretion disk surrounding the black hole. And there's 3 different things that can happen. Okay, so here's our black hole. Okay. And let's say our black hole is spinning in this direction. Okay, the accretion disk can spin in the same direction. This is prograde spinning of a black hole. It can spin in the opposite direction of the black hole. Okay, this is retrograde motion of the black hole. And the last scenario, anyone wants to take a guess? That's right. No spinning. If you have a non-spinning black hole, just a stationary black hole. Now, in most astrophysical situations, these don't exist because during the formation process of the black hole, matter is swirling around, stuff is moving, and angular momentum is conserved. So when the black hole finally forms, it almost always has some kind of spin. It's almost never spinless. Okay. Okay, boring stuff. Let's skip that. So, moral of the story is that to characterize a black hole, we only need these 3 parameters, right? We need to know how heavy it is. That impacts how big the black hole gets. We need to know how much charge it has. Usually, real black holes don't have charge. They neutralize very quickly. And we need to know how much spin it has. Now, real black holes actually spin very fast. They spin almost close to the speed of light. And so, anyway, that's what you see there. Okay. Good. So those are the 3 parameters that characterize the black hole. Now let's get into the interesting stuff, which is how do clocks and rulers change when you get close to a black hole? So this right here is a clock, right? And I don't have a black hole with me right now, but I did laser print one. So let's take a look at this. Oops. Okay. So here's my 2D black hole. And what you see here, this is a laser cut property, but now it did. When I bring my clock close to the black hole, you might have heard that clock slow down near a black hole. But what does that mean? And you might have heard that people, well, depending on the person, but people spaghettify when they get close to a black hole. What does that mean? Here's what that means. Okay, so here's what that means. Okay, so I'm going to show a little simulation here that shows a black hole in action. So, oops, no, wrong person. Let's see if I can pull it up here. Okay, so this simulation will show you how time changes as you go close to a black hole. So I've got a rocket here, and this rocket has some clock attached to it, right? Hopefully you can see this. And I've got the event horizon of the black hole right here, okay? Now the reason this rocket is not falling straight into the black hole is it's got engines turned on, so it is accelerating, even though it looks like it's stationary. So, okay, so let's add some clocks and let's see what happens, okay? So I'm gonna add a few clocks here, okay? And I'm going to make the clocks increasingly close to the, oh, there he goes, okay. Wish I could do that to some of the PhD students here, but okay, let's reset all of these clocks here. And let me add a clock that's very far away. Okay, and okay, so I'm going to reset all of these clocks, and you can see which clock goes the fastest. Oh shit, wrong button. The challenges of live presentation. What can I say? Okay, so first let's synchronize all the clocks. Okay, so what you would see if I had done this nicely is that this last clock closest to the event horizon ticks time slower than this top clock. Okay, this last clock is reading 12, while this one reads 16, for example, right? So this was Einstein's big discovery, that gravity itself can slow down how fast time ticks. So going back to my presentation, so that's what happens when you approach a black hole. Clocks tick slower when you're deeper in the gravitational well. Now, if you're wondering why that is, you can ask me later. I can dive into the details. But back to black holes. That's a brief summary of black holes. Now I'm going to talk about where we come in. How am I doing on time? Okay. Okay, so black holes were first predicted by the big man himself, the legend, Einstein, when he published his field equations. So Einstein's field equation is this. Okay, it took me 22 years to finally understand this bad boy. But the idea behind the field equation is remarkably simple. Okay, what the field equation tells you is on the right side of the field equation, you have the letter T. On the left side, you have the letter G. I know that means nothing right now, but they will in a second. This T represents your mass distribution in space. It's called the energy momentum tensor. So you're basically telling Einstein's field equations, where are your objects located in space? And Einstein's field equation will then tell you, how does space respond to those masses? How does space bend and curve in response to those masses? Okay, so Einstein published his field equations in 1915, but he didn't have a solution to his field equations. As they say, incompetence. No, I'm joking. Please, don't kill me. So this is Carl Schwarzschild. Oh, write it on the board. Okay, well, that was unexpected. But Carl Schwarzschild was the first person to discover a solution to Einstein's field equations, and that solution was a black hole. Clearly, ChatGPT was not working, so I'll have to compensate for that. So this is the solution. Wow, okay. So the solution that Schwarzschild found is called the Schwarzschild metric, and it tells you everything you need to know about a black hole that is non-rotating. So here's the Schwarzschild metric. It has a timepiece, it has a space, oh god, wow. It has a space piece, and it has an angular piece. And these three pieces will tell you how time slows down as you go closer to the black hole, how rulers will stretch as you go closer to the black hole, and how angles will change as we approach the event horizon. So the time component is this. The space component is the exact same, but with a -1 here. And the angular component is just this. What this is telling you is that as r, the radius here, approaches the Schwarzschild radius, time will start to slow down. This temporal parameter will become smaller and smaller. What this is telling you is, notice this is a -1 here. What is that -1 telling you? Does anyone see anything? You can shout, it's okay. Shout it out. That's right, this -1 is telling you there's an inverse, and so that inverse tells you that when you're at the Schwarzschild radius, you have a 0 in the denominator. So there's a singularity in the event horizon, at the event horizon. So this tells you there's a singularity, this tells you how clocks slow down, and this tells you how angles change as you approach a black hole. That's what Schwarzschild discovered, and what ChatGPT couldn't. So the next step in the history of black holes was taken by Robert Oppenheimer, or Big Oppie as I call him. And what he discovered is that if you have a sufficiently big star, when that star starts to collapse, there's no known physical force that will prevent the star from collapsing to a single point of infinite density. And that single point becomes the singularity of a black hole that will form from that sufficiently massive star. And then in 1960, Roy Kerr discovered a solution to Einstein's equations, not for non-rotating black holes, but for black holes that are spinning. And then in 1975, Stephen Hawking discovered that black holes are not black. They have a temperature. Why? Because any object that has an entropy, Stephen Hawking discovered black holes have an entropy proportional to their area. Any object that has entropy will have a temperature. Why? Does anyone have an idea? If we write down the first law of thermodynamics, it tells us that there's only two ways you can change the energy of a system: by adding heat or by doing work. Now, if you add heat to a system, that'll increase the entropy of the system. And by how much? By this much. So whenever you have an entropy, this equation tells you by the first law of thermodynamics that you'll have a temperature. And if you have a temperature, that means you're emitting photons. Any object that has a temperature emits photons. And so that means black holes are actually not so black because they're emitting these very long wavelength photons that we call Hawking radiation. So that's what Stephen Hawking discovered in 1975. And then in 1998, Andrea Ghez, who won the Nobel Prize in Physics in 2020, only the fourth woman to receive the Nobel Prize in Physics, she and her team at UCLA discovered that stars around the center of our galaxy, of the Milky Way galaxy, oh, shit, oh, sorry. She discovered that stars around the center of our galaxy were moving way too fast around an object way too dark for it to be anything other than a supermassive black hole. And so that's what Sagittarius A star was. Okay. And then in 2015, the LIGO team discovered that when two black holes are spinning around each other in a kind of cosmic death dance, then they coalesce into a single black hole and create a gravitational wave. Okay, great. Lesson learned, I'm not going to put videos. So, and then in 2017, this is the ultimate finale, the Event Horizon Telescope created the first ever picture of a black hole. This is the black hole M87 star. It's not at the center of our galaxy. This is a black hole that's about 1,000 times farther from us than Sagittarius A star, but it's also a lot bigger than our own galaxy, and it's a lot more active than our own Sagittarius A star. That's why the Event Horizon Telescope team decided to take a picture of this first. And so now, what I want to discuss today, well, if I have any time remaining, when do we end? I forgot. 3 minutes? Oh, 3:50. Oh, we got time. Oh, I should have gone slower then. Okay, so so today I'm going to be talking about BHEX, which is the next step from the Event Horizon Telescope. And BHEX proposes to take a picture of a black hole from space instead of from observatories on the Earth. And this picture of a black hole will have a much greater resolution than the picture taken in 2017, because in space, you don't have to deal with the Earth's atmosphere. You have to deal with a lot more. So you lose something, you gain something. But at the end, the hope is that you can isolate the photon ring of a black hole. This photon ring, if we look at this picture here, oh, by the way, there's pizza. It will be superseded by this black hole. So what you see in this diagram here is 4 things. First of all, you have the event horizon of the black hole right here. That's this. And then you have this accretion disk. Oh, shit, no, that's 4. Okay, this is the accretion disk surrounding the black hole. This is all the matter and gas and dust that's spiraling around the black hole. But that's matter. There's actually a gap between the event horizon and where stuff orbits the black hole. Why is there this gap? Because this gap, this is the last place anything with mass can orbit a black hole in a stable circular orbit. That's why this is called the innermost stable circular orbit. But if you don't have any mass, like me, no, I'm joking. Does anyone know anything that doesn't have mass? That's right, photons. So if you don't have any mass, you can orbit much closer to a black hole, and that's what you see over here at the second thing. Okay, and what is this last thing? I'm going to explain that on the blackboard, and that's going to help us understand this picture over here. So let me erase this. Oh, by the way, if anyone has questions, please interrupt. Okay, so, wow, this is wet for some reason. Okay, here we go. So here's a black hole. Wow, this looks like a hot mess. Here's a black hole, and it has some Schwarzschild radius. And what I'm going to do is I'm going to throw photons at this black hole. And I'm going to wait until one of the photons comes back to me. So here's what I mean. Okay, so let's say I'm all the way over here. I'm on the Earth, and I've got a telescope. So here's the Earth, okay? I've got some kind of telescope I'm looking through. And I'm shooting one photon at the black hole. Okay, I've shot this photon to hell, essentially, because it's just going to go to the event horizon, cross the event horizon, and hit the singularity, right? Okay, that's fine. Now, I shoot another photon. Okay, it keeps going in. I haven't learned my lesson, apparently, which is to increase the impact parameter of this photon. The impact parameter is how far I'm shooting my photon from this line of symmetry of the black hole. Okay, so this is my impact parameter. So obviously anything up to here, the Schwarzschild radius of the black hole will just go into the singularity. But now if I shoot a photon a little bit up, it's not going to orbit the black hole. It will get sucked in a little bit like this. And any future photon will also get sucked in, but at progressively later times. So the question is, how far you have to shoot your photon so that the photon eventually traces a boomerang orbit back to your telescope? Because that's what you want, right? You want to see the photons arriving back from the black hole. That's what you're seeing here. The photons that are just able to escape the black hole. It turns out the radius at which you're able to do that is 2.6 times the Schwarzschild radius. So it's a little bit outside the photon sphere, but it's inside the innermost stable circular orbit. So that is what you're seeing in this picture here. Let's keep going. Okay, so to summarize this brief history of black holes, we started in 1915 with Einstein, and we saw Schwarzschild discovered the first solution to Einstein's field equations, and Oppenheimer showed that any object with a sufficient mass, there's no physical force, no known force that can stop it from collapsing to a singularity. Roy Kerr discovered a solution to Einstein's equation for rotating black holes. Hawking discovered that black holes have a temperature. Andrea Ghez discovered that there's a black hole at the center of our galaxy. Roger Penrose discovered that if you cross the event horizon, there's nothing you can do to stop going into the singularity, because space and time actually flip inside of a black hole. If you guys have questions about that, happy to discuss more. LIGO discovered that two black holes spinning around each other in a kind of cosmic death spiral create gravitational waves. The Event Horizon Telescope captured the first picture of a black hole, and the next step in this century-long exploration of black holes is BHEX, the Black Hole Explorer satellite, which hopes to take a picture of a black hole from space rather than from here on Earth. Any questions? Feel free to interrupt me, because I think I don't have enough slides, honestly. That's why I'm asking. Oh, yes.
Well, you talk about the relation between gravity and how gravity slows down the clock.
Yeah, absolutely. That's a great question. Okay, let's. You know what? I've got a Desmos simulation just to answer that question. So let's take a look. So that's a great question. First of all, what's your name? Zane. Okay, great. That's a good question, Zane. So the question that Zane asked is, how does time change around a black hole? If I'm understanding right. So in this picture, you see, in this graph, you see two things. First of all, the x-axis is telling you how far away you're from a black hole. The y-axis is telling you how much time slows down as you approach the black hole. And here I have three graphs. One graph, this red graph, is telling you how much time slows down for a clock that's orbiting a black hole, how much time slows down for a clock that's stationary around a black hole, and how much time slows down if you're very far away from a black hole. So, to clarify further, let's take this out and let me draw a different diagram to explain. So here we go. Here's our black hole. Okay, it has some short shell radius, 2m over c squared. And what I'm plotting in this picture are three clocks. One is a clock that's very far away. This is called a coordinate clock. Okay, so let's see, very far away, and it's green. So here's my clock. Okay, very far away from the black hole. So let's say that r is much greater than r sub s. Then I have my stationary clock, this orange clock, that's just hanging around the black hole. Okay, so let's say here's my stationary clock, and it's not moving, right? How's it not moving? Why isn't it falling into the black hole? Because it has rockets. So it's accelerating, right? So it has to accelerate so it doesn't fall in. So here's our stationary clock. Let's say that it takes some time, t sub b. Let's call this clock t sub a. And finally, I have a orbiting clock in red. Oh, there we go. And this orbiting clock is at the same radius from the black hole as the stationary clock, but this time this clock is actually orbiting the black hole. And let's say it takes some amount of time, t sub c. Okay, so what we're seeing in this picture is that, let's take a look at some distance from the black hole. Let's say let's see, does anyone have a favorite number from 0 to 5? Zain? Zain?
3.
3, okay, that is a good, maybe, okay, 4. Nice, okay, thank you. So let's take a look at what happens to these clocks at 4 times the short shell radius, okay? So this radius here is 4 times the short shell radius. Okay, so what you're seeing is that the orbiting clock takes the least amount of time, the stationary clock takes the second least amount of time, and the coordinate clock takes the most amount of time. So that means that, so this clock, for example, if this clock says, okay, 30 seconds has passed, then this stationary clock will say only 20 seconds has passed, and this moving, orbiting clock will say only 10 seconds has passed. Of course, the exact values are here on the plot, but that's the idea. If you're moving around the black hole, you take less time than if you're stationary around the black hole. Now the question is why? That's because if I write down the short-shelled metric, but only the time part, if I just write down the time part of the short-shelled metric, okay, then you'll see that this time part tells me how much time slows down as I approach the event horizon. But if I'm orbiting the black hole, then I have to add another part. I'm forced to add this angular term. And this angular term reduces my the total amount of time I take. Why does it reduce the total amount of time I take? Because you can see it has a different sign from the time term. Now you might say, why does it have a different sign? It's because if it didn't, it would no longer be a solution times 10 field equation. Now you might say, why would it? Well, that I don't know the answer to. So, is that, or is that, okay. Yeah, yeah, absolutely. Any other question? Yes? Oh, well. Oh, that's a great question. So, okay, that's a great question. So let's see. I say it's okay. I keep repeating it's a great question because I don't know the answer. But now that I think about it, so you said zero time passing, right? So let's try to take a look. What happens? When do things stop ticking? Okay, so what I've plotted here is y equals 0. Y equals 0 is when time stops ticking, right? Because the y-axis is time. Let's see when time stops ticking. For the orbiting clock, time stops ticking at 3 times the short shell radius. That's where the photon sphere is of the black hole. If we go back to our picture here, the photon sphere is where light makes its last pass around a black hole. That's the place where light can just barely escape the gravitational fields of a black hole. That's where time stops ticking for an orbiting clock. Oh, thank you. You don't have to. But for a stationary clock, time stops ticking at the event horizon itself. So that means, for example, this clock that's stationary, it's ticking time, right? It keeps on ticking time. But as soon as you put this clock right at the event horizon, the amount of time that will traverse is 0 seconds, no matter how long you're waiting all the way here. So the amount of time that passes for this observer at the event horizon, if he's not orbiting the black hole, will be 0 seconds at the event horizon. And finally, when does time stop ticking for the coordinate clock? You can see time stops ticking for the coordinate clock at r equals 0, which is the singularity of the black hole itself. So really, the answer to your question is three-tiered. It depends on time stops ticking for who. Okay, if you're very far away from the black hole, if you have a coordinate clock, then time stops ticking according to the Schwarzschild metric. Time stops ticking at the singularity. But if you're a stationary clock at some given radius from the black hole, as you approach the event horizon, then time stops ticking. And if you're an orbiting clock, then time stops ticking at the photon sphere. Now you might ask, why? Oh,
What if you had the rotating, the orbiting clock, hit the photon up, tracking time, and then you had the stationary clock pass it? They
okay.
stop. They're still ticking with time until they hit the limit.
Okay, well, could you say that again, please?
Yeah. So there's
Yeah.
like the space between the photon sphere and the horizon.
Okay.
So when the orbiting clock hits the photon sphere, it
Okay.
stops ticking. But what happens if the stationary clock passes them?
Oh, okay, okay. Wow. Okay. So let me try to answer that with a diagram. So let's see if maybe I'll keep the black hole here. Let's see. I'm gonna try to figure it out. I don't know the answer off the top of my head, but let's see. Okay. Great question. So okay, so we have one clock that's stationary. Okay, let's say this is our stationary clock, and one clock that's orbiting. Okay, here's our orbiting clock, and so you're saying the orbiting clock passes into the event horizon?
It hits the photon sphere when it stops ticking. It's time to stop ticking.
Right.
But then the stationary passes it. But before the stationary clock hits the event horizon,
Uh-huh.
what do they see for the orbiting?
Huh. Uh, let's see. Okay. You got me there. I'm not actually sure. Let's see. So here's the photon sphere at 3 times the Schwarzschild radius. So okay, so let's track it. So okay, now I'm approaching the photon sphere, approaching. Time is slowing down for the stationary clock. And now the stationary clock is at the photon sphere. Okay. And the orbiting clock has stopped taking time. Okay. So I might have to chew on it, but it's a great question. Yeah.
Like,
Yeah.
do you think they would still, like, just your guess, would the stationary clock just observe the orbiting clock just frozen? As they pass through towards the event?
Okay, so one way to answer that question, I'm not sure about the complete answer, but one way to answer that question is now we have to think about special relativity in addition to general relativity because this stationary clock is moving at some velocity and it's watching this orbiting clock. So for example, if I have let's say I have my two clocks. Okay, so let's say that this is the stationary clock that's moving and it's watching the orbiting clock, which has apparently stopped at the photon sphere. So if um, if I'm in a reference frame that is moving with this clock, then I'll just see this clock. By the way, this is a light clock for anyone who a light clock is just like a regular clock. It's just a photon bouncing back and forth between two mirrors. So if I'm moving with this clock, then I'll just see the clock, the photon go up and down like this. But if I'm in a frame where this clock is moving with respect to me, then what I'll see is that the photon traverses a greater distance. It goes like this and like this. So I'll see that time has slowed down for this light clock as opposed to this light clock. So just a draft answer to your question on the spot might be that as this stationary clock is moving towards the photon sphere and it looks at the orbiting clock, the orbiting clock has stopped ticking. But according to who? This is zero time according to the observer who's infinitely far away from the black hole. This is stationary time. This is zero time according to a coordinate observer. So when this stationary clock passes this observer, you would probably have to account for time dilation because of the relative velocity between the stationary clock and the orbiting clock. But that's just a very hazy answer. I'd have to think about it, but it's a great question. Yes?
So regardless of where you are in the black hole, if you were holding a clock
Mm-hmm.
and like moving at the same velocity as the clock, it would always show the same time, right?
Say it again.
So like, the only reason why time slows down here is because the clock is moving with respect to the observer. Like, when you draw a work.
Oh, are you asking why time is slowing down as you approach the black hole?
Yeah.
That is a good question. It's not because.
Or like, is it only slowing down with respect to an infinitely far away observer?
Okay.
It's slowing down with respect to us, not with respect to the system.
Yes.
Okay.
But I should clarify. That is a great question. I should be more careful with my language. So let me clarify. So okay, this is good. So here. Okay. So I'm gonna draw a clock on the blackboard. Okay. This is gonna be a light clock. Okay, a light clock is just a clock with two mirrors and a photon bouncing up and down between the mirrors. Okay. So this is, for example, one period of a light clock, right? So the photon goes up, and then it hits this mirror, comes back down. So we might say that, okay, 1 second has passed for this light clock because the photon has made one full cycle. But that's according to an observer for whom this light clock is moving. If you're moving along with this light clock, right, then the light clock is not going to be moving. Instead, so here, it looks like the photon has gone like this and then come back down. Because for this observer, the clock is moving, right? So imagine you've got, okay, this is obviously not to scale, but you can imagine the clock is moving with respect to you. On the other hand, if you've got a situation where you're moving with the clock, then it seems like the photon is just going up and then down. It looks like the photon is traversing a much smaller distance. This is what we call the proper time of the clock. This is the time experienced by an observer who's actually watching the clock, who's carrying the clock with them. It's also called the wristwatch time because it's just the time you would see if you were moving with the clock. Okay. On the other hand, this is called the coordinate time. This is the time passed for the clock according to an observer who watches the clock move. But I should have been more careful in describing this. This time that you see plotted here, this is the proper time experienced by an orbiting clock. So this proper time, this is the time according to someone who's with the clock. So I did make a mistake. That's right. So thank you for asking that question. Otherwise, I wouldn't be forced to clarify. So for the orbiting clock, this time that I'm plotting, this is the proper time. This is the time according for an observer who's literally with the clock at all times. For the stationary clock, it's the same thing. This is for an observer who's with this clock, who sees the clock as being stationary. This coordinate clock is a clock that's infinitely far away from the black hole. This is a clock that's with an observer who's watching the black hole from very far away, and they have their own kind of wristwatch. That's the coordinate time. It's the time according to the watch of an observer very far away. These two times are the proper times of the clocks for an observer who's moving with these clocks. So the distinction is very tricky, but that's why Einstein won a Nobel Prize. But great question. Yeah. Yes. Yeah, yeah, absolutely. Yes. Okay, so you asked how the Kerr metric changes the interferometric signature of the black hole? Okay.
Yeah.
Wow, that's tough. That's a great question, and it's a tough one. So, so first, let me write down. Let's go to the Kerr metric to see how it changes the signature. So, okay, let's go to Kerr here. Okay, so the Kerr metric takes into account the spin of the black hole, right? And you can see that the time component from the Schwarzschild metric stays almost the same. You still have that 1 over 1 minus 2m over r. That tells you how much time slows down. Now the metric is no longer what we call a diagonal metric. It has cross terms. You see time and space mixing with each other, t and phi. So that's the Kerr metric. Now, how does that impact the interferometric signature? I'm going to answer that with the third part of the talk. So, but it's a great question, which I have only the partial answer to. But any of them? Oh, I got 10 minutes. Oh, sorry. Okay, very quickly. Okay, so how do you image a black hole? Right, so, okay, well, did we talk about these? We talked about the singularity, event horizon, photon sphere. So imaging a black hole is like taking a picture of a donut that's on the moon. So you need basically a very big telescope to take a picture of a black hole. But you can't use an optical telescope because our black hole, for example, is hidden behind shrouds of interstellar dust. So you need to move to infrared or radio telescopes. And so if you have a black hole that's emitting radio waves and you have a radio antenna to pick it up, then that radio antenna picks up those radio waves. It constructively interferes those radio waves. And what the job of the radio telescope is to combine each of those signals into one constructive interference. And so when the radio telescope does that, it gets this spike in its data, and that spike corresponds to a radio source. This might be a black hole or some kind of other object that's bright in radio. But if you want to take a picture of a black hole, it turns out you need a radio telescope that's the diameter of the Earth, which is impossible. But the same job can be done by lots of tiny telescopes all around the Earth if they combine their data using radio interferometry. So now that's what the Event Horizon Telescope collaboration is. It's 8 telescopes all around the globe that use radio interferometry to combine their data and create a telescope that's the size of the entire Earth and therefore take a picture of M87 or Sagittarius A star. How does it do that? Like this. So that's how you take a picture of a black hole. And so BHEX, the idea for BHEX is to put this in space. And so I reached out to the BHEX team this January to ask if Brown can participate by putting a second satellite in space that integrates with the main BHEX telescope. That's what this proposal here is for. And so we'll be pitching, me and Graham will be pitching to the BHEX team in June. Before we do that, what we're trying to do is, okay, I ran out of time, but what we're trying to do is create a coalition of all the Ivy League space organizations that can collaborate to create this second auxiliary satellite to BHEX. What would a second satellite do? It would create a much sharper resolution image of the black hole at the center of our Milky Way galaxy. So that's it. Graham is gonna take the 6 minutes. Yes.
This also just a brief thing. So we were discussing when we were going through this proposal and seeing how we can contribute to this incredible mission of getting better readings on a black hole and just in general. We were looking at kind of two different ideas. One of the things is creating another copy of the or a smaller version, or some sort of contributing telescope that would be actually gathering data, that would be looking at the black hole, or that would be in some way boosting the of the large. Another thing that we were considering, more on the smaller scale and not necessarily exclusive of the other idea, is a small sat that would fall more under the domain of CubeSats that each individual school kind of works on. The main part of the BHEX satellite that there are a lot of single failure points, but the main part that I think is, I don't know, not necessarily high risk, but definitely a challenge is the communication between the satellite and the Earth. The original picture of a black hole required literally petabytes of information, so thousands of terabytes, and they had to be put on disks and shipped physically because it was impossible to transmit that much data. So the way BHEX gets hundreds of gigabytes of data a second down to the Earth is through technology modeled in the T-Bird satellite from the Lincoln Group at MIT. And it is going to revolutionize space communication in general with direct linking the ground and satellites without having to deal with the slowness of radio waves that are traditionally used. However, this technology right now is based on the technology that will be used in the next satellite is based almost entirely off of this CubeSat. This CubeSat right now is about a 6U CubeSat, weighs 12 kilograms, and points itself. It's basically a self-contained, self-sustaining thing that sees where it needs to go on the ground and transmits. And it only does it from about 300 kilometers. BHEX satellite is going to be much further, thousands of kilometers away. So they're going to have to make a lot of modifications to this tech for this mission. They're going to have to create a mechanism on the BHEX satellite that already struggles from weight constraints as any satellite does. It's going to be a massive 500 kilogram satellite, and it needs to fit within certain massive grant specifications and funding parameters. So they're going to have to figure out a way to point the instrument, and then also part of BHEX and their observation window relies on the fact partly of the satellite being able to see the black hole and have a good observation window without other celestial bodies blocking it, things like that. But another consideration is actually weather on Earth. Because the BHEX satellite is so constrained by mass and money, it doesn't have any internal storage. It can't store any of its data, so it has to get rid of it immediately. So part of the constraints for observation are having satellite or downlink stations on Earth available that can be seen by the satellite. Now, because this is such a high bandwidth transmission, it can be messed up by things like weather. It's coded and made to deal with the fading of the atmosphere that messes with the transmission. However, adverse weather over one of the many tropical downlink sites could mess with their observation design. So to cut to the chase, one of the things that we were thinking of is potentially modeling, but is instead of forcing BHEX basically to always be in constant communication with the ground whenever it needs to observe, using a technology that is already commercially proven. Right now, satellites in orbit are communicating with each other at super high bandwidth, transmitting hundreds of gigabytes of data per second. The SpaceX Starlink constellation uses lasers to communicate with between the constellation. And these terminals are relatively small, on the order of like a couple kilograms. So the idea suggests putting, instead of forcing VHEX to have a direct downlink of the Earth, putting these commercially available, sold, tested, they call it plug and laser instead of plug and play, but whatever. Having something like that so VHEX can transmit its hundreds of gigabytes per second of data to a sort of buffer satellite that can hold in internal drives. Again, it's still in the form factor and size of a CubeSat. All of the like super valuable petabytes of data that it can then transmit to other satellites like the SpaceX network, or try or be a model of T-Bird, and then eventually establish its own connections with ground stations. So the idea is giving VHEX a lot more room to maneuver and potentially freeing up a ton more observation windows so that it isn't reliant on some very finicky connection to the ground and can transmit whatever data it gets whenever it can possibly observe a black hole, a sort of buffer satellite that holds all of the data and then safely, on its own time, transmits. And this requires like very little modification to this T-Bird satellite. Essentially, it would just involve smacking like a laser terminal already sold by SpaceX on this. This already has a 2 terabyte buffer, and it's built into the whole system to be able to take in a bunch of data quickly and then burst it down to the ground whenever it can get a possible back. So this is just sort of another possible way to contribute to the X, and is potentially on the order of a CubeSat launch initiative grant as opposed to maybe a large amount.
Yeah, that's it. Um, moral of the story: if anyone here is interested in working on a black hole satellite, I'm the guy. We're the guys. So just feel free to contact us. Get in touch. If you just Google my name, don't Google my name. Please don't Google my name. But I'm right here. So feel free to reach out if you're interested in this project. And yeah, hopefully this was exciting. So yeah. Okay. I'll stick around if anyone has questions, whatnot.